Yeah, I'm going to talk about my work on Shannon capacity. So you may know Claude Shannon as the father of information theory. He was also a member of the Institute in the 1940s. He asked the following question in the 50s. We take a communication channel. So this is something I can write down as a graph, like this. So it has inputs, 5 inputs, and 5 outputs. Now this channel is very boring. It just sends 1 to A and 2 to B, etc. So that's a very useful channel because the receiver actually knows what I meant to send. Now imagine that your channel has some noise, and this noise, it's probabilistic. So 1 goes to either A or B with some probability, etc., etc. So let me just give this example, like this. So we're giving this channel, but we want to communicate without any error. So if the receiver now receives A, he doesn't know if it comes from 1 or 5. So what we can do is to do perfect communication without error is to restrict the input, for example, to the elements 1 and 3. Right? Then if we agree to use only these inputs, then the receiver can know what we have, what we meant to send. Right. So this is a good set of inputs. Now we don't want to use the channel once. We want to use the channel multiple times. For example, if we use the channel twice, we can send pairs of inputs. And if we use the following set of pairs, 1, 1, 2, 3, 3, 5, 4, 2, 5, 4. Then it's not hard to verify that any 2 pairs is distinguishable. Because if you receive, 1 and 2 can be sent to the same element B, but for example 1 and 3 can't. Right? So in this way, you can any given pair you can distinguish. So let's simplify this problem a bit. So instead of these channels, we want to talk about graphs. So we forget about the outputs and we only write down the inputs 1, 2, 3, 4, 5, and we connect them whenever they can be confused by the channel. Yeah, so 1 and 2 can be confused because they map to the same output B. And then what we're looking for is really an independent set. So we're looking for a subset of the vertices, for example 1 and 3, that are not connected. That's what we want to do if we use the channel once. Another useful object is the adjacency matrix, which we all know. So it's a 5 by 5 matrix in this case. I do want to have 1s on the diagonal. And I put 1s for the edges, like this. Right. Okay, so let's formalize what we're trying to do. We define the independence number, alpha of G, as for general graph G as the size of the largest independent set in G. I want to define a product of graphs, G times H, by taking the adjacency matrices, taking the Kronecker product as matrices. And I want to define the sum of graphs by taking the direct sum of the adjacency matrices. All right. Shannon proposes to study the following parameter. This is an H. What was your question?
G is the graph.
Yeah, say you have 2 graphs, G and H.
Oh, G is H.
Yeah, these are 2 graphs, yeah. So Shannon proposes to study the following. We take the limit of n going to infinity of the independence number of g to the power n to the power 1 over n. And it turns out, it's not hard to see that this is equal to the supremum over n of alpha of g to the n to the power 1 over n. And this is the so-called Shannon capacity of g. Okay, so the goal is to understand the Shannon capacity, and the Shannon capacity tells us what is the amount of information we can send over our channel, such that the receiver can, without error, see what we were trying to send, and we normalize it in a way that we look at it as if we are using the channel infinitely many times. Yeah. So Shannon computed this function for all graphs of size at most 6, except for this 5 cycle. And he conjectured, based on his computations, that the Shannon capacity is additive and multiplicative under these operations. So that's his work. So a little bit later, there were more people working on this. One of them was Lovász in the 70s. He computed the Shannon capacity of the 5 cycle, C5. This guy. And he showed its square root of 5. And for this, he introduced a new technique called the Lovász theta function, which is denoted by a small theta. So, in the same year, Hamers proved that theta is in fact not multiplicative. And Alon, later in the 90s, proved that it's also not additive. Okay, so, so much for the conjecture. So the conjecture is false. Good. And just to give you an idea of the status of how hard it is to compute this parameter.
Does one know how far it is away from being multiplicative?
That's a very good question. I don't know. There are results about, so I've been thinking about it. I don't have a good answer yet, but yeah, it's a good question. Yeah. To give you an idea of what's the current state of the art, there's a result of Polak and Schrijver. So the 5 cycle is solved. This result is on the 7 cycle. They didn't quite solve the 7 cycle. So the upper bound, again, comes from the Lovász theta function. And they have a lower bound which is close, but not quite there, which is like 3.25 or something. Okay, so for small graphs, we can't. We don't know how to compute. Is there a question?
Where's alpha?
Where's alpha?
I got theta twice.
Yeah. Yeah. Let me make this into a capital. This is a capital theta, and this is a small theta. Right. Okay, good. So this is like a short history, and there's much more work on this problem. Let's talk a bit about what I did. Right. So instead of studying graphs, I want to study functions on graphs, and more precisely, I want to study the following set of functions that I call X. So X is a set of all maps F from the set of all graphs to the real numbers, non-negative real numbers, such that the following four properties hold. I want my functions to be multiplicative, additive, I want them to be normalized just by saying that f of the graph with one vertex is 1. And the fourth property is that, maybe it's not so important to understand this one, but let me say it. If there is a graph homomorphism from G bar to H bar, which are the complement graphs, then I want f of G to be smaller than f of H. Yeah, so of course you can think of graphs as a semi-ring, and then these are semi-ring homomorphisms, and there's the pre-order on them. So these are the monotone semi-ring homomorphisms on graphs. So it's not hard to see, let me write it as a lemma, that for any f in X, we have that the Shannon capacity of G for any G is at most f of X. So in particular, we could minimize over all these f's in X and try to get a good upper bound on the Shannon capacity. Does it actually reach the Shannon capacity? And that's my result. The result is yes, it does. So fix a graph G, then the Shannon capacity is equal to the minimum over f in X of f evaluated at G. Of course, so if we want to understand Shannon capacity, it would be sufficient to understand X. So the big question is, what is X? And we don't know. But, so even without knowing X, so we do know some things. We do know some elements in X. For example, this Lovász theta function turns out to be an element in X. Okay, so all these tools that were developed, they give elements in X. Lovász theta function, the technique that Harmers used gives rise to an element in X. We don't know if we have all elements. So, okay, so we don't know what X is, but still we can.
Do you have an idea about how complex X is?
There are some structural results about that it's connected, for example, and there are some convexity results. Yeah, I don't know what else to say about it. But, yeah.
Ways of generating other elements in X?
Yeah, there's by some kind of convexity result. Yes, you can interpolate in a certain way. Yeah. All right. We don't know X, but we can still use this result to learn other things about Shannon capacity. So let's talk about that. All right. So let me maybe also mention, I think of this as a duality statement, because the Shannon capacity, I define it as this limit, but it's also this supremum. So you're trying to maximize something, and the result is that it's equal to like a minimization over some other set. Okay? So it's a duality, except we don't know what X is. So what are some nice consequences that follow from this duality? I want to talk about 3 of them. The first, which was mentioned to me by Holtzman, is that Shannon capacity is locally additive if and only if multiplicative. So let me explain what I mean by that. So I mean that if you take any 2 graphs, G and H, then the Shannon capacity of GH equals Shannon capacity of G times Shannon capacity of H, if and only if they add. So if and only if Shannon capacity of G plus H equals Shannon capacity of G plus Shannon capacity of H. The proof of this is actually pretty simple using this duality. I don't know when I started actually, but.
That's a good question. I don't know.
So,
I think you're close to the end.
That's good. So this is I give this as an exercise. Let me just mention that if you have this statement about additivity and multiplicativity, you also see that the results of Harmers and Allon are equivalent. And maybe the last thing I want to mention here is that the
So with the counterexamples that are non-different to Hamilton, you've shown they're the same.
I think they're the same. Yeah. Yeah. So the third thing I want to mention is that the Shannon capacity is not attained is in general not attained at a finite power. This was well known, but this gives you can do a nice proof using this duality. So what I mean is, right? It's defined as the supremum over these powers. It could have been that you find a solution to this for a fixed constant n, right? Which is the case for the 5 cycle. Okay. It turned out that that's not the case. That was well known. Let me just give that as a last thing. So I use this statement. Let's take the Shannon capacity of C5 times one vertex. Well, C5 times one vertex is just C5 under the product that I defined earlier. So this is the Shannon capacity of C5. And the Shannon capacity of one vertex is just 1, so that I can also put here. So the Shannon capacity of these two guys is multiplicative. And we know that it's multiplicative if and only if it's additive. So now I want to look at this sum. Yeah. So this will be the Shannon capacity of C5 plus 1. And we know that this is square root of 5 plus 1, which you cannot write in the form a to the power 1 over n for any a and n. Okay, so this showed it's not attained at a finite power. Right. So yeah, let me finish. So this is about graphs. There is a more general theory which applies to these graphs, and it also applies to tensors, which I've been studying a lot. That's relevant for matrix multiplication and problems in combinatorics, like the capset problem. We've had some recent results on the quantum version of this theory for graphs. And as I mentioned earlier, Peter Vrana has a result on the asymptotic spectrum of graphs, this set X to be connected. Yeah, thanks.